Hello everyone, welcome to this video. In this video we will be building up our APL knowledge so that we can implement the forward pass in the neural network. Don't worry if you don't know yet what this means. In this video we are going to talk about simple scalars, and simple arrays in APL, and we are going to discuss the enclose, disclose, and reverse primitives, and we will also talk about idioms. So if you are very familiar with all of these, feel free to skip this video. Otherwise, sit tight. Let me talk about what scalars are. So for starters, I'll be defining a vector with a bunch of numbers. And the things that constitute the vector, the elements of the vector, are called scalars. Why? Because those are the building blocks of the vector itself. If I were to define a matrix, say a 2 by 2 matrix with zeros, these zeros over here are the scalars of this matrix because those are the building blocks of the matrix itself. But now suppose I'm creating a larger vector which is composed of the first vector and then maybe the matrix and then the matrix again and then the matrix again and then the vector. So this is double V. What are the scalars of the vector? Well, the elements of the vector are this vector and then this matrix and then this matrix and then this matrix and then this last vector. So these are all scalars. And you can see here that APL makes it easier for me to recognize that these are scalars because it boxes them with these lines. If for some reason, or if your interpreter doesn't box them for you, maybe you should try and type in closing brackets and then box on. You don't have to do it caps lock, you can just write box on and then try this again. So these boxes tell you what things are scalars. Okay, but maybe, well, hopefully you can look at this scalar over here, so this vector, and you can look at this scalar over here, this 4, and recognize that they, even though both of them are scalars because they are elements of a vector, they look different. And in fact, these very basic scalars, so numbers or characters, those are the simple scalars. Those are the most basic elements that you can use to build your arrays. And all other scalars, so things that are boxed like this over here, so this, I can select only this element in here. Yeah, so this box is a non-simple scalar because it's a scalar, but it's not a single number or a single character. And sometimes you will want to expand a vector of non-simple scalars. For example, I have VV over here, and now I want to concatenate it, or I want to catenate it with another copy of V. So I can just go ahead and catenate double V and V, right? Except not, because V is itself a vector, and what APL sees is I'm going to catenate two vectors, double V and V, and so what we are creating is a vector with all the elements from the left vector and then all the elements of the right vector. And that's why 0, 1, 2, 3, and 4 get split up in different boxes. But that's not what I wanted. I wanted to create another copy of this. So I need to tell catenate that V is actually to be seen as a scalar. And in order to do that, we use the enclose primitive, which you can type with APL Z, as in zip. And if you do so, actually let me go ahead and execute only the zip of V, you can see that V gets boxed. So this means V is a vector. Sorry. This means that enclose of V is a scalar and V by itself is a regular vector. Now if I go ahead and take double V and then catenate it with the enclose of V, then I get my intended behavior, which is this. So we can enclose, okay, but we can also disclose. If I have enclose of V, let me call it E for enclose. Now I have a vector that is enclosed, so I have a scalar that contains a vector inside, and the way to disclose this, the way to access the vector inside the scalar, is with the disclose primitive, which you can type with APL X, as in extract. So if I go ahead and disclose E, I get the vector again. But actually, the disclose primitive can be used to do other things. Well, in particular, it has a dyadic case, so you can give it an integer here and it will do something else for you. But you can also use disclose in an array and it will return the first element of the array. So in particular, if V is a vector, disclose of V gives me the first element of V, or maybe if I disclose double V is a vector, so I'm going to get the first elements of double V. And now, what if I wanted to get the last element of a vector? Well, I know how to get the first. And now if I teach you how to reverse a vector, then the last element of the vector is the first element of the reversed vector. Right? So I have 0, 1, 2, 3, 4 over here. This is my V. I don't know why I wrote it down explicitly. Now if I type APL shift 5, I get this symbol, which looks an awful lot like APL shift 6, which was transpose, if you recall. And transpose flip a matrix along this slanted line, along this slanted axis, and reverse does exactly the same thing. It's going to flip whatever you give it to the right, and it's going to flip it like the symbol itself says. So if you use a vector, the vector gets reversed. And actually this also happens with APL shift 7. So you can see that now you have an horizontal line. So if you have, say, 2 by 2 matrix with the numbers 1, 2, 3, 4, and if you use APL shift 7 on that, APL shift 7 on that, you see things get flipped along an horizontal line. So yeah, now we can reverse a vector, and so now I can get the last element of V, which is the first element of the reverse of V, with disclose. So I can go right ahead and type in APL X and then reverse of V. Notice that as I type this gets colored differently. And that is because the disclose of the reverse is what we call an idiom in APL. And idioms are common combinations of APL primitives that have a specific meaning and that can be greatly optimized if you are to interpret them as a whole instead of as their separate parts. I don't know if you have any computer science background or not, but reversing a list, it's usually O of n, so it's an operation that usually takes as long as the number of elements in the list. So every time you want to pick the last element, like this, you having to reverse the whole list to only extract the first element, then it's going to be very expensive. But the interpreter can look at this and say, oh, so we just want the last element, and the interpreter can go right ahead and pick it instead of having to reverse everything. And this gets significantly faster as V grows, and I will show you just that. So if you are in a hurry, feel free to skip the rest of this video. Otherwise, let's explore something interesting. Let me go right ahead and define a large vector of numbers, let's say 10,000 numbers. By the way, I don't think I've ever used this. This is iota, and it works like this. It's easier to see than to explain. It generates the first n numbers. And then, actually now I have to say this, yours might be different. Yours will probably generate a number starting with 1, and that's because of quad IO, which is something that controls how indices are managed and generated, either 0 indexed or 1 indexed, but that's beyond the point. So I have a vector with a lot of elements, and then I'm going to use closing bracket runtime dash c, as in I want to compare the runtime of the two expressions I'm going to give you next, you, the interpreter. So let me open double quotes. This could also be single quotes, but then whenever you use character vectors inside these expressions, it becomes weird, so I just go with double quotes to avoid any confusion. And now let me pick the last of v, and so this is what I'm saying is faster, because the interpreter reads the peak reverse or the disclose reverse as an idiom, and then I'm going to compare it with, well, essentially the same thing, except I don't want the interpreter to recognize this as an idiom, so I have to break it in some way, and I think the simplest way to do it is to wrap this in a diff. Okay, so this does exactly the same thing as the first expression, except that I'm wrapping the disclose primitive in a diff so that the interpreter can't see this is an idiom. Then I go right ahead and press enter and give it some time because it's running both expressions a couple of times. And then I'm going to get presented with this graphical representation of how much longer one approach took. And you can see here, so this is the average time it took for this to run. I'm not exactly sure, I think these are seconds. So 7.4 to the power of, times 10 to the power of minus 8 seconds to pick the last element of v. But if you are to reverse v and then pick the last one, it takes this long. So this is approximately 65 times longer. And this was just 10,000 elements, and the elements themselves were really simple. They were just integers. Let me go right ahead and make this vector 10 times bigger, so 100,000 elements now. Let me go right ahead and compare the runtime of this. As you can see, the idiom performs about the same speed, at about the same speed. No, actually, it was faster this time. So the vector increased, and this was faster in this particular instance. And then, well, reversing and picking the first got slower. And there's a huge increase in speed. So that's what APL idioms are. And in the next video, I'm going to be teaching you a little bit more of APL, and then we'll be implementing some more of our neural network functions.